Hello, my name is Kristiane, and today I will be presenting my results of Lab 1, which is about constant velocity. The objective of this lab was to analyze and compare the position as a function of time of an object moving in a constant velocity. We used Tracker to record our observational data and computer modeling to record our predicted data. I analyzed the motion of a volleyball rolling across the floor in a straight line, as you can see here in a preview of Tracker. So why do we do this lab? This lab is to help us understand how Newton's second law can help us show and predict different components of an object's motion, such as position and velocity. Here I included Newton's second law, which is also called the momentum principle. This formula is the one we used to make our predicted model, which is the final velocity is equal to the initial velocity plus the net force on our system divided by the mass of the system times the change in time, which in this case is the time interval between frames. And our system is the ball. Here we can see a preview of my results. This graph is comparing our observed position of the ball with the predicted model position of the ball. We will discuss later why there are differences between these. Now let's discuss the first part of this lab, which was to track the motion of the object using the software Tracker. I chose to analyze the motion of the ball along the frames 46 throughout 71. These frames captured when the ball was mostly rolling at a constant velocity. If I had chosen to analyze frames that were earlier on in the object's motion or at the end of the video, those frames would have captured an acceleration or deceleration of the ball. And in this lab, we are assuming that the ball is moving at a constant velocity, which means that the net force on the ball is zero. This also means that our initial velocity will be equal to our final velocity. To calculate the initial velocity, I calculated the average velocity between the first two time steps. As you can see, my ball was moving in the negative x direction. So what would have happened if we would have flipped the axis? Well, this would mean that my ball would be moving in the positive x direction now. This would result in the sign of my velocity and the sign of the position to all be positive. Their magnitudes would not change, but their sign would. Now let's analyze how I did the coding for the predicted model. First of all, we plugged in the initial conditions, which is that the mass of the ball is 0.26 kilograms, the position of the ball, which is based on our observational data, and the initial velocity of the ball, which we just discussed and is also based on our observational data. Now, to calculate the updated velocity after each time step, we have to use Newton's second law. Now, to calculate the updated position of the ball, we use the formula. Final position is equal to initial position plus the velocity times delta t. This formula can only be used in this case where f net is equal to 0. Here is the result of our predicted computer model. Now, let's compare our observational experiment data, which is the blue line, with the predicted computer model data, which is the red line. As you can see, they are almost identical, but nearing the t equals 0.4 second mark, the model position is overestimated. This means that the slope was less for the experiment data, meaning that the ball was moving slower in our observed data. This could be due to factors that were not accounted for by the computer model, such as air resistance, friction, gravity, and any movement from left to right of the ball. In conclusion, even though my computer model's prediction for the ball's motion was highly accurate, it was not identical to our observed data. This was due to the following reasons. Number one, like I previously stated, the actual velocity of the ball was not constant. This is due to external factors acting on the ball, such as friction, gravity, air resistance, and normal force of the ground on the ball. We assumed that the net force on the ball was 0. But could we have actually calculated the number of pushes and pulls that would give us a net force of 0? Well, no, because just as we could have had two forces with the same magnitude acting on opposite directions, we could have had 4 or 6 forces with equal magnitude but opposite direction. So there's no way of determining actually how many forces are contributing to a net force of 0. Number 2. Because tracker requires me to mark the position of the ball manually, it is subject to human error. Overall, this lab was very educational to show how Newton's second law can help us predict motion. Thank you.